Good scientific afternoon, everyone, and welcome back to another MC Science session where we are today going to be talking about crude oil and fractional distillation. We will be today answering the following questions. What is crude oil? How was crude oil formed? What is fractional distillation? And why do different hydrocarbons have different uses? So, as always, if you have any questions along the way, um, do ask away and we will get going as we are. So, in a previous session, we have talked about why carbon is special, what hydrocarbons are. We've also looked at why hydrocarbons are used as fuels and why it makes useful fuels. And today, um, when we look at all these, where all these hydrocarbons come from, we start to understand that crude oil um, is very useful for multiple different things. So we're going to today then think about what crude oil is, how it's formed, and all these other things. So let's get delving straight into this. So my first question for you all is, um, or my first part is, how was crude oil formed? So to kind of ask, well, how was crude oil formed? We've got to kind of actually start to delve into um, the fact that crude oil began forming millions of years ago, and it's made from the remains of tiny plants, tiny animals, microscopic organisms called plankton. And we still do have to even today plankton uh, around. Um, I would assume it's probably this same species, but obviously um, there might have been some evolutionary changes. So, well, what happened to all of them uh, organisms, plants, animals? Well, they died and they sank in a lot of cases to the bottom of the seabed. And then layers of mud, sand, stones, all sorts of things piled on top, and it created heat and pressure over millions of years. And so, with this, then, the other key thing is, and we talked about it on Monday, um, if we were to look at how creatures and stuff, what normally happens to us, we're normally broken down when we die into all different bits, and our nutrients and everything um, leaks into the soil and stuff like that. And in this case, some of you as an organism isn't broken down, and so we call it a fossil fuel because a fossil fuel is a fuel formed from the remains of ancient living things. And so a fossil fuel is not something that we can just make in a human lifetime. And there are three main fossil fuels that I'm hoping you should know of some of them. Um, and our three main fossil fuels are coal, which formed mostly from ancient plants, oil, which formed mainly from marine organisms, and natural gas, which often forms alongside oil. So if I drew you a diagram, um, So if you picture the seabed along the bottom, and under that seabed, so here's our seabed and our water and some plant life and stuff. Um, what we actually then do is, as the stuff's been crushed under loads and loads of stuff, we end up forming like a little pocket. I've just realised I'm drawing this off screen currently. And in that pocket, this is where the organism that's been crushed and everything starts to get broken down and form this crude oil. And with forming this crude oil, as it's getting crushed and stuff, we end up with um, a little natural gas pocket here. Ooh, let me let me place it down. Um, And so this is what normally happens is we end up with our natural gas, like a little pocket above our crude oil. So this is what we look at. So modern technology and things like that nowadays will assess this and see if um, it is producing that there is this gas pocket, if you will, and we can then go from there basically and figure that out. So, yeah, this is what we expect to see. And obviously, then humans come along, and we would come along and um, bore down into all of this and start draining it out and suck it all out. And what we actually normally do is we'd actually have a secondary tube. And because oil is less dense than water, what we actually do is we pump water in underneath, basically, and the oil then raises to the top, and we get then all the oil out through a second spout, if you will. So we have one pumping water in and one taking the oil out in that kind of motion, if you will. I'll draw it like this. And this is a very, and I'm saying this as if it's like 100%. This isn't always the case. This is purely a sometimes happens, sometimes don't. Depends on the scenario. And obviously, again, we can tap off the natural gas as well. Now, if you're not a subscriber to our channel, I do ask that you follow us. And we run these sessions 3 times a week. So we have biology on a Monday, chemistry on a Wednesday, and on a Friday we run physics. And we are going to be increasing to GCSE as well from September, and we're also going to be adding primary school level work to our sessions as well. So currently, the content that I'm going through is what you would be expected to learn in year 7 to 9. So just to throw it in timescale up here. So I've already said, that um, it was millions of years ago. As a timescale, dinosaurs were 230 to 66 million years ago. Okay. Some oil deposits began forming before dinosaurs existed. And so this is actually one of these kind of things that some people don't always realize or understand is that many, you know, some cases dinosaurs were involved in the making of crude oil, but it's not all. And that's a really important thing to understand. So, um, but I do find it quite ironic that I don't know why it's suddenly shifted me all the way over there. I do find it quite ironic that we make plastic dinosaurs out of their remains. Um, so many of our North Sea oil reserves. So if you don't know where the North Sea is, um, let me show you this on a map. Um, so here is the North Sea. So the North Sea is anything, uh, kind of, if you will, um, London upwards up to Scotland, and it comes all the way through into this area here. So this is the North Sea. So many of our North Sea um, area uh, comes from reserves 150 million years ago, and we have huge amounts of evidence nowadays as well, just to throw it out there, that basically uh, the UK was, we had like marshland and stuff like that all in here, and actually all of this was all once land as well. So all of this was land and marshland and everything, and then eventually over time it faded away. And so and I'm sure that it would have probably been the same between Ireland and the rest of the UK. And eventually it started to wash away, and and more got water in, and then eventually sea levels rose and everything, and washed all this away, and we ended up with seas here and the English Channel as well. And this is how humans would have originally have got to these countries. Um, so oil as well um, is forming naturally today. This is one key thing. Okay, there will be out there new reservoirs and stuff starting to form, but it takes too long to replace the current stuff that we are using up. Okay. And so one of the biggest things that people normally say is, well, can we not make more? It's like, well, yeah, more is being made, but it takes millions of years. So it's not something that we can just start, or start like um, pointing out, you know. So I've got multi-choice now for you. Um, and with this multi-choice, what I will ask you is, crude oil is formed from what? Volcanoes, ancient marine organisms, metals, or rocks only? And if you would like to comment in the chat or on the comment section of YouTube, that would be amazing to tell me what you think. Um, all work that we do here at MC Science is free of charge, but we do accept donations when it comes to these online group sessions. So do get in touch with us if you would like to make a donation towards our regular videos and the work that we are going to be doing here in Plymouth to make a better community. Now, if you did get it, it was, of course, B, ancient marine organisms. There we go. So the next thing that we can then start to look at is, well, what is crude oil? Okay, so we've said, well, what makes crude oil? Let's now look at what is crude oil. And by us looking at what is crude oil, many think crude oil is just like a oily substance that you would have seen um, that we, use for car engines and stuff. But crude oil is actually a mixture of hydrocarbons. It isn't just a single substance. It's a mixture of lots of different hydrocarbons. And if you remember what a hydrocarbon is, a hydrocarbon um, is a substance. So let me write it here quickly. Hydrocarbon equals carbon and hydrogen elements only. So it is a compound that is made up of carbon and hydrogen only. And if it's small enough, we are able to ignite it really easily. Um, when they get longer chains, so when I'm talking about chains, let me um, do another drawing. So when we're looking at um, hydrocarbon chains, what we normally have, oh, that's a bit too thick. Let me make that a little bit. So we would normally have a whole load of carbons all linked together like so. Um, and with having the carbons linked like so, we'd have hydrogens on the end of each of these. So hydrogen can make one bond because it has one valency, which basically means it has the ability to make one single bond with something else. Carbon is in group four. It has four valencies. It's able to make four bonds. Hence why we can see here um, bond one, bond two, bond three, bond four. And with that, then um, what we can do is just keep adding more and more uh, carbons in. And by adding more and more carbons in and having more hydrogens here, we can get basically longer and longer chains. All right, this is what's happening. Um, and I'll put there, etc. So that I don't have to keep drawing miles and miles and miles. And so this is happening all the time. Okay, these are hydrocarbons. And I weirdly quite like the fact that that bulges in the middle and like gets bigger. So if they're really small, a typical hydrocarbon that is super small um, is methane. Now, methane, if you think of me um, as a individual, methane is actually just one single carbon. Okay, and it's attached to four hydrogen. So this is what it would be structurally. It would look like this structurally. And if I was to write its chemical formula, it would be CH4. So one carbon, four hydrogens. And then we can start looking at other um, compounds in that as well, like propane, butane, methane, and propane we normally use in barbecue cylinders, and so you get to see them on a regular basis. Now, we could also look at things like petrol hydrocarbons. So obviously we use petrol in cars, and then we've got another chemical that's another type of hydrocarbon called bitumen, and bitumen is used on roads and roofing. So it's that black tar-like substance that bonds um, the stuff together when we make tarmac, basically. Um, so when you think of bitumen and then compare that to methane, that is quite a difference in a substance, but they all come together and they all make that individual substance called crude oil. So depending on the length of the chain of carbons, depends on whether or not um, you're going to have a very flammable substance that's short, small chains, or a really long substance that is thick, tar-like, and is a lot harder to ignite. So there are, and I'm just saying this, there are thousands of different hydrocarbons, and in general, we kind of we've named a lot of them, but they do, you know, some of these chains. That's why I put etc. here. We don't normally write etc., but just for today, I have. Um, we kind of just normally leave it as a line showing that direction, but we can just keep adding more and more carbons, and just get a bigger and bigger chain. And we can then start to, I've done this on a two-dimensional level. We could start to look at what we call mods and build three-dimensional structures as well, um, which makes life that little bit more um, interesting and different. So if I then asked you the next multi-choice question, and I'll just move me over here. My next thing is crude oil a pure substance, one hydrocarbon, a mixture of hydrocarbons, or a metal? And if you have said it's a mixture of hydrocarbons, you are correct. Well done. And so again, we can start to then figure out, well, okay, these are all really long chains of things, Andy, like spaghetti, if you will. If you got a whole load of spaghetti and you broke some of it up to make smaller spaghetti and you add it all in a bowl together, all mixed together, cooked obviously, because you're not going to get the same result if it's all dried. So cooked spaghetti all together, all tangled together. Well, how can I separate that so that I've got methane on its own, so that I've got petrol, so I've got propane? Well, this again is what we start to do as a thing, and we use a separating technique known as their boiling points. So the boiling point of a and their molecule sizes, because each hydrocarbon has a different length chain, we end up with a boiling point that differs. Even though all of them are only made up of hydrogen and carbon, because the longer the chain gets, have more and more bonds, we end up with a higher and higher boiling point because it takes more and more energy to break all of them bonds. So, if it is a small molecule or a small hydrocarbon like methane, ethane, propane, butane, they always have a much lower boiling point. They evaporate really easily. And if you're not 100% sure of what evaporation means, it means that it's, you know, um, turned into a gas state and it is released to, apologies, the surroundings, and it has that high. Our medium size hydrocarbons, well, our medium sizes, they're normally our petrol, our kerosene, our diesel, and they're liquid at room temperature. Hence why petrol stations, we just like pour them in and into our petrol tank. And if we were looking at the larger hydrocarbon chains, well, again, depending on what it is, they're normally thick and sticky and they have a really high boiling point. So this is why you will see them generally being heated if you're ever watching one of the lorries. Uh, Hold on, let me get a. Whenever you see a tarmac lorry, um, they have the hot roller, and it's because of that high melting and boiling point. There we go. Um, and you can see there, look, the steam coming off of it. So they would get this tarmac there super quick, whilst it's still a bit more on the malleable side, and then the roller will go over the top of it and compact it all down at the same time as applying the heat to make sure it's able to melt and bond with the other bitumen in the areas as well. So it really is as simple as the bigger the molecule, the higher the boiling point of our hydrocarbons. Now, how then, well, can I separate these? So if we were looking at how I can separate these hydrocarbons, well, we use a process called fractional distillation. And here is one of my images from the MC Science website, mcscience.co.uk, which you can find more information um, on. And we separate all of these fractions using fractional distillation. Now, this is a simple, small setup where we could do it in a um, lab. So we're not expecting fractional distillation to actually look like this. Actual fractional um, distillation industry wise. So this would be a simple bit of glassware, but industry wise, nope, don't save the image. Um, Industry wise, we would be this kind of scale. So in a lab, we'd have just the glassware like this. In industry, it would be huge plants like that, which really makes you kind of realize how things change. So, first of all, we've got to start applying a bit of that heat, haven't we? And by applying some heat, we have some crude oil getting heated, and some of our smaller hydrocarbons with that lower boiling point start to heat up as well. And by them heating up, they're able to evaporate. So step one is heat up. Now, in general, we would use a electric heat an element here because um, obviously by using flame it could ignite. In industry, um, because it's one of them kind of things that they would use, they would generally actually um, use some sort of oil or something like that, something flammable to ignite it. But they have it in a complete different way. So step two um, is the vapor enters a fractional column. So here we are. Now, you can see here, this is our fractional column. So we've got the gases all down here. We've got our mixture, as we can see here on the image. And then it starts to break away and come up here. Now, you'll notice that it's green here, and then up here I've drawn blue. So it will then be blue beyond. Now, this is what the fractional column actually does. It slows down um, the compounds by having loads of little bits sticking out. So what they've done with the fractional column is increased the surface area. By increasing this surface area and having loads of things sticking out, basically the small little hydrocarbons are able to zigzag through really easily. And as it gets bigger and bigger as a hydrocarbon, they find it harder and harder to get through here. So this then there'll be another color here that is starting to come up and get caught a lot more. And so when you're doing this as a lecturer and actually observing this, you do see a load of it pouring back down into the um, flask as well. So like I said, we have then got these fractions coming up, and they're traveling up the fractional column, which is there to separate the fractions via their boiling point and their size. Okay, so as they're traveling up, we have a thermometer up the top, and we can then generally would have a fraction like this. We come along the inside into what is known as the condenser. Now, you'll notice on my condenser here, and this is the reason why I actually drew it like this, is my condenser, um, for all condensers, and they love to ask this as an exam where they say, draw the arrows on a condenser. And you actually have to draw an arrow going in at the bottom and say water in, and you have to draw an hour, arrow going out the top and say water out through the top. And with that, this is because this condenser, the water actually like swirls around the outside and then leaves. So it's kind of like a big straw with a belt around the outside of it to cool everything down. So all of these hot particles then are coming along. They're colliding with this cold water surface. And by colliding with that cold water surface, instead of still pinging around and having lots of energy and being like, yeah, look at us pinging around, they start to cool down and turn into a liquid again. And they'll trickle along the bottom here, and they'll drip into the container that they're being sent towards. And this is then the reason why the water goes out the top is so we're getting rid of that thermal energy that's been transferred from the oil into um, our water as fast as possible. And by bringing in the cold at the bottom, it does this. If it was the other way round and the cold water came in the top and went out the bottom, it would actually be less effective because all the heat would remain in it until it came out the bottom. And by doing it this way, we get rid of that heat straight away. And that's actually a really important thing, and they love again to ask questions about it. So step three, um, we actually, like I said, the vapors would enter the column, and with entering the column, um, it's hotter at the bottom because that's where we are heating the bottom, and it's cooler at the top. And eventually, the really long chains will get to the top as well if they've got the capability. I'll show you in a minute a different diagram. No, explain what I mean by that. So hydrocarbons condense at different heights. So what we would actually have if this was a true fractional column is we'd have pipes coming off here at different levels. And basically, by having the pipes at different levels, it will condense at its own specific temperature and trickle then down accordingly. So when we're looking at fractional distillation and we look at an example um, where I like this picture. Um, from the Royal Society of Chemistry. This is what we'd actually be looking like in industry. So they've got their heating at the bottom, it's coming up, trickling, and then the really small ones trickle off and come down here, and then the really thick, gloopy bitumen and stuff like that all trickle out at the bottom. and that's what would actually happen in industry. But like I said, in a lab, it is slightly different because we need it to be that little bit different. So fractions are produced. Um, Top of column are refined gases. All right, so up here normally are gases. We then have our petrols, our kerosenes, and the longer the chain gets, the further down the fractional column we get, with our really long, gloopy ones right at the very bottom. And one of the things that I then love to tell my students to do is this little practical here. So this is a nice little layers practical. So get some water and oil and bit of food coloring so that you can see the clear difference between the two. And oil and water generally form layers on top of each other, and by you forming these layers, you're able to um, create this um, layered effect. And the amazing thing would be is seeing how many layers you can build. So, for example, get like something like golden syrup, put that at the bottom. Because golden syrup should sit at the bottom, then water will sit on top of that, and then oil will sit on top of that, and pure alcohol will actually sit on top of oil because it has a different density, and you'll end up with a whole load of layers. And the reason why you add your food coloring and stuff is because it makes it that little bit more easier. Let me see, because I did at one point do this experiment, and I swear I've got it on my phone. Bear with me a minute. Mm-mm-mm-mm. Because I can then kind of show you an example of this, and I think it will make a bit more sense to you to as a bit of fun. Um, so, oh yeah, this is where um, I've just realised some of the videos I've made in the past. Oh, leaching of colours, that's not almost there. Um, bear with me, bear with me. That's when I met a load of pigs um, at a farm that I was doing a bit of work at. I can't find my image, which is a shame. It'll be here somewhere in all of my photos of the different experiments that I've done. But I just can't find it now, which is a bit of a shame. But with that, we can still figure these kind of things out. Ooh, no, that's my disappearing cross experiment. And it just weirdly looked very, very similar. Uh, do 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 do. So, oh yeah, that's where I get the egg inside the conical flask without breaking it. Um, Found it. Right. Um, Let me see if I can put this on here. There we go. So here's one I made earlier. And this is different viscosities, so different densities of substances. So this is basically, imagine this when we're separating different things. So this is golden syrup. There's a metal nut down there. So a grape will float on top of golden syrup, but it won't float on water. And then um, where's that water? That might have been something even else. That might be water, I think. It's been a little while since I've actually remembered what I did. And then you can see the alcohol on top with the oil there. So bit of polystyrene there, and different layers, and you can basically drop different things in and see which layer it floats to as well to see which density it has, if it has a higher or lower density as well. And it was such a fun little experiment to do with um, some of my students. Um, Now, what I would then recommend, so a little bit of history, like we do in our sessions as well, because it's good for you to know the little bit of history, because sometimes these kind of things come up in one of these quizzes that you can go to. So the first commercial oil well was drilled by Edwin Drake in 1859 in Pennsylvania, USA. This began the modern oil industry and in doing so transformed transport, manufacturing, and energy production around the world. As a career, if you've found what we've talked about today interesting, you could become a refinery process engineer. So what you would do is operate and improve oil refineries, design fractional columns, improve fuel efficiency, develop cleaner fuel technologies, ensure industry processes are safe. Um, you would need the following grades, to which, bear with me. There's quite a good range of paths into this now. So you would need your GCSE combined or triple science, maths and English. That's a standard thing for most careers and jobs now. You would then go on to A-level chemistry, maths or physics, or a BTEC in engineering or applied science. Um, Most colleges offer applied science, and it gives you a range of the different sciences. You can then go on to a degree as a chemical engineer, or you could go down the apprenticeship route and level up through that direction instead. Salary wise, it is decent salaries. As an apprenticeship, you would get 18 to 25,000 a year. When you graduate from a uni, you would get 30 to 40,000. As you become more experienced, again, this goes up more and more, and you would become eventually senior management or consultancy role where you would go to 80 to 120,000 plus a year. Um, the kind of places you could work with such a career would be oil refineries, chemical plants, fuel companies, energy companies, and environmental technology firms. You would need to be able to problem solve, have some math skills, science understanding, teamwork skills, safety awareness, and attention to detail. Um, Little did you know as well, a single barrel of oil contains 159 liters of oil, and with this can be turned into dozens of useful things, including petrol, diesel, jet fuel, lubricants, plastic, medicines, cosmetics, and even some clothing fibers as well. If you think anything made of polyester, that is normally from crude oil. Um, our key words today have been crude oil, hydrocarbon, fossil fuel, fractional distillation, boiling point fraction, refinery, and bitumen. And before you go, we have some curiosity questions for you, to which I like to ask at the end of every one of my videos. And again, comment in the comments at the end. If crude oil eventually runs out, what will replace it? And why don't we simply use one fuel for everything? And could scientists one day create artificial crude oil? Thank you so much for joining us. And again, do join us on Friday for a bit of physics, and I will see you again